I would like to introduce Professor Omar, that he's an associate professor of Mondragon University and also the CEO of and founder of Avesta Battery and Energy Engineering. So his expertise is through all the value chain of the batteries. So you can see here, you can see his presentation, and then after the presentation, you can ask questions if you wish. Okay.
Great. Thank you very much. Can you hear me well?
Yes, perfect.
Great, perfect. So today I will take you with me through this session where we will go about different topics which are related to batteries. First of all, I will start with an introduction. Then we will move to battery pack designs for automotive and non-automotive applications. And then we will look further to aspects which are related to safety, fast charging, and sizing of the solutions. But first, let's start with the introduction one. As you know, that the electrification market is increasing, and when we are speaking about electrification, we speak typically about battery electric vehicles, BEV, plug-in hybrid electric vehicles, PHEV, and hybrid electric vehicles. And you see here that the yellow line is going to increase over the years, and the expectation is that by 2040, at least 55% of the market share of the sales will be fully electrified vehicles. That is quite increase. And you see here that the increase of the battery electric vehicles will increase as well. However, the increase of the PHEV will be quite limited. So from that perspective, that's something that you have to know. And when we speak about electrified, it means you need an energy source, and this energy source is typically a battery source. And that is also what you see on this graph, that lithium-ion battery market for stationary transportation and electronic devices over the coming years is going to increase, not in a linear way, but more in an exponential way. So 2017, the market size was around 120 gigawatt hour. And the expectations are by 2027, we will have a market share. So the installed or the production capacity should be increased to 1,000 gigawatt hour. And the new studies are even indicating by 2030, we should across 2,000 gigawatt hour. What does it mean? Increase of the production capacity by factor 9. And that's a reason also why you see often in the news everywhere in the world, and new factories have been popped up here and there and so on. And this even is still not enough, because we need many gigafactories to deal with all these needs. The most important that you have to see is the yellow bar, which is actually representing the transportation, and that's a big gap that will require the energy. For stationary, it will increase quite slightly, and the electronic devices market is a typically quite very stable market. Don't expect too much explosion. What is important to know, if we reflect this need with the localization, then we see actually China, which is represented actually by red bars, here is a circle, are actually dominating the market. Not from now, from long time ago, and that was related to the fact that the Asians started quite with the battery technology from early in the beginning with making batteries for electronic devices. And you see that even by 2028, still China will have a very big of the market, and that's something that we have to take into account, because still the production capacity over 70% is coming from China. Europe in 2018 was quite very small, and 2023 we see some increase. In 2028 we are expecting around 200 gigawatt hour battery production in Europe, but it's still not so much compared to China, which will be around 630 gigawatt hours. Now, when we speak about electrification, we have also to understand and to reflect that to needs and which are the requirements and specifications. And when we speak about specifications and requirements, typically we have the durability, which is expressed in the distance in kilometers, or the durability time. And if we look to this graph, which is representing different types of application, typically for the passenger cars, we are here. 300,000 kilometers, 8,000 or 10,000 hours. That is typically what is the requirement for this car. But look for the city buses, for instance, the requirements are completely different. We are speaking about 50,000 hours, around 1 million kilometers. For heavy duty trucks is completely another aspect, 1.5 million kilometers and around 30,000 hours. So from that perspective, the design of energy storage or powertrain of energy storage system is depending on the application requirement and specifications. And that's also what you see here reflected in these regards. Now, that means quite a lot on an implication on the design and the requirement that should to be taken into account, and also the selection of the right energy storage technology. Now, since we are speaking about batteries, we have firstly also to start thinking what is a battery and how it's working. So typically a battery has a cathode, an anode, a membrane, electrolyte, and so on. And when you discharge that, you get a transfer from ions, because lithium-ion technology is based on transfer of ions, where ions goes from the cathode to the anode, so from cathode to the graphite, which is this part. And for the charge is for the discharge is the same structure which you have, and you have a difference in the voltage, and this difference of the voltage, which we call actually the battery voltage. There's a difference between the anode and the cathode, and of course it looks quite very simplified, and that should not be complicated. However, if you look deeply to those type of materials, they are composed of particles with specific diameters, size, and in order to keep all these particles together, you need binders. And you need also to have improved conductivity, you need conductive carbons or elements for that. So in reality, the concept is much more complicated than we could believe in that regard, and that's why there is huge development in the field of battery technology. Now, if we transfer that to as we call it, a Ragono plot, which is representing the specific power in function of specific energy, we can see here that there are quite a lot of technology that could be actually used for an electrified vehicle. In the beginning, we started with lead acid technology. Then we moved to nickel cadmium, nickel metal hydride, which we are still using for hybrid batteries like in the Prius. And then we moved slightly to lithium-ion technology. As you can see, for lithium-ion technology, this area is quite very wide. It is actually starting from 60 watt-hour per kg, and it's ending somewhere around 250 watt-hour per kg. In the meantime, we are even close to 270 watt-hour per kg. Now, what does it mean? Lithium-ion is just a general name, which is representing different types of chemistries. And those chemistries can be either higher power-oriented or high energy-oriented. You cannot have both. It is physics which are related to the materials selection, modification, and optimization, or you will optimize for distance, or you will optimize that for power, which is actually representing the acceleration. And if you want to have a combination of both, you should to maybe select something here in between. What you also can do is actually hybrid, making hybrid concept of energy storage by lithium ion with high power technologies like electric double layer capacitors, for instance, but just something for your information. Now, when we speak about batteries, as I said, lithium ion is representing the family of chemistries, and everything is depending what you are using on the cathode level and the electrolyte level and the anode level. And the most used one are lithium cobalt oxide, which we typically use it for our electronic devices. So all your cell phones, laptops are composed of this battery technology. Then we have what is integrated in the Tesla nickel cobalt aluminum, Ca. So N stands for nickel, C stands for cobalt, A stands for aluminum, and then NMC, which is integrated in many platforms like BMW, Volkswagen, Volvo, and stands for nickel manganese cobalt. Nissan Leaf is using lithium manganese oxide. Tesla in China or BYD are using LFP, lithium iron phosphate. LTO is more used for high power application, fast charging application, lithium titanate oxide. And typically all the solutions are using graphite as an anode, a liquid electrolyte. But you could also have same configuration where graphite is replaced by silicon or silicon carbon. For which reason? To increase the specific capacity of the anode in order to increase the overall energy density. And then we have something else which we call it lithium polymer batteries, and that is actually what is integrated in the Blue Solutions technology, which typically are operated at higher temperatures. Now, if you look to all these characteristics of batteries, no one is perfect. Every battery chemistry has a specific characteristics, and you see, the more you have plus, the better the solution is. The more you have minus, the worse it is. And you are selecting the chemistry depending on the application needs, or better mentioned, in functions of your requirements. What do you want to have at power level? What do you want to have at energy level? And what do you want to have actually at lifetime and safety? So from that perspective, the selection of the battery should be done accordingly and not in a different way. For that perspective, LCO for electrified vehicles cannot be used. The only what can be used is a combination of those materials. But what we see as a main product standard is NMC, LFP, a lot, except for Tesla, which is still using NCA batteries. Now, if we reflect that to a vehicle and solution for the vehicles, we have to understand actually what is electrified vehicles. So for electrified vehicles, let's start from the right side. We have an electric powertrain where you have an electrical motor and large electrical and battery. That's simply illustrated. But you have also a plug-in hybrid, which has still large battery in the range of 10 to 12 kilowatt hour, as you can see it here, and still composed of a conventional powertrain, where you have still internal combustion engine, which is also driving. So it's a hybrid concept where it can drive electrically for a specific range or specific modes, and then also it can turn in the conventional mode for specific operations. And then you have hybrid, solution where the battery capacity is quite very small, and it's a continuous interaction between the internal combustion and the electrical motor. And of course, battery solutions for all these applications are different. This is high power oriented, this is high energy oriented, and this is something in between. That's something we have to understand. Now, when we go to electric vehicles, you can understand that the battery here is fully a part of the vehicle design, or is integrated fully into the chassis. And that's something that you have to understand, and this is not something which easily can be designed, not from the mechanical, not thermal, electrical, insulation, safety, etc. And that's quite very complicated process behind that, and that you should to understand. So typically for electric vehicles, battery is an essential part of the powertrain, but also from the chassis point of view. Now, when we speak about the different types of electrified vehicles, we have to understand that there is also the voltage levels which are associated to those vehicles are also different. And that's what you can see here. So mild hybrid can be 12 volts, 48 volt, or even high voltage. We have solutions which can be based on 100 volt, 400 volt, but more and more we are also going in the direction of high voltage. And with high voltage, we typically speaking not anymore about 400, but 800 volt, and you will see afterwards what is the reason behind. So take into account moving from this safety voltages to this higher voltage is not only creating opportunity, but also creating a lot of challenge, which you will see afterwards. And that's also affecting your another components and system that you are going to integrate, like the generator, electrical motors, inverters, etc. So it's combination of different elements that you have to take into account, and so on. Now, and here in those slides, I want to give you a couple of examples of some electrified vehicles, which are already commercially on the market. The first one is a Porsche Taycan, where the voltage is 800 volt, for instance. Why? For the reasons because they want to charge that with 250 kilowatts DC, and to keep the charging time quite very limited, around 30 minutes. You see here the battery capacity is 90 kilowatt hour, which is not relatively so high, and that means the charging rates are quite extremely high. Here, Fisker, 800 volt, but the charging power is 350 kilowatts. So, and the reason is actually to reduce further the charging time, 15 minutes, which is getting closer to the time that you need to fill in your tank for your conventional vehicle. And the battery capacity, of course, is much larger, which is equal to 140 kilowatt hours. Another one, Chevrolet, 800 volts, battery capacity 32 kilowatt hour. Another one, Aston Martin, 800 volt, charging powers 100 kilowatt hour, battery capacity 65 kilowatt hour. Another concept, of course, the requirements are completely different. Kia, 800 volt, charging power 200 kilowatts, charging time 20 minutes, and that is, you see, there is a very clear push from the automotive industry to go towards 800 volts, where you see the reason for that afterwards. Audi supercar prototype here, 800 volts, 350 kilowatts, with a battery capacity of 95 kilowatt hours. Now, You saw in the previous slides that typically voltage for electrified electric vehicles or is plug-in hybrid or fully electric vehicles are in the range of 400, 450 volt. However, it's interesting to increase the voltage levels towards 800 volt or even higher for the different reasons. Firstly, when your voltage levels are higher, the current will decrease, then your cables are much thinner. Your components or systems will become much more smaller and lighter, like the motors, inverters, etc. And that is and also efficient. The heat that will come out of it from all these components will be much less, which is more interesting from the thermal management. Lowering manufacturing costs because they will be smaller. They can be also, the battery can be used much faster, charged much faster, which also key aspect, and also the power associated to that could be much higher. So there is a general trend from the automotive sector to go towards 800 volt as much as possible. Now, if you look to this graph, what can happen in the scenario if you have a battery which is, let's say, for instance, composed of 400 volt, you want to double this voltage to 800 volt, for instance. It means that high voltage will not affect as such the cell current. However, it will lower the current through output through the full systems. And the reason is just this simple equation. The power is still equal to the voltage multiplied by the current. For the same power, if you increase the voltage, of course, your current will decrease. And also the losses, associated losses, will decrease as well, since the current rate will decrease as well. So it's more interesting to go from this scenario to this scenario where you could have benefits more in power and more in the losses that can be reduced accordingly. Another aspect is, which is related actually to the components. If you have batteries which are connected in series or in parallel as an where you typically do that through bus bars, you need also to dimension the bus bars in function the current that you want to that should flow through the bus bars. For the same power, for instance, if your voltage are high, 800 volt compared to 400 volt, what is going to happen? Yeah, your current rate will be almost the half of at 400 volt, and that means also the bus bars will be much thinner, smaller, lighter, which is also quite a very an advantage aspect that you should take into account. Same aspect for cabling. Should not explain that much. If your current rate is half, your cable thickness in principle is also half, and that is also reduction of weight, reduction of volume, etc. And that's also what you see here. So the cross-section area is in function of the current rate. So take into account if your current rate will be 200 amps, and if you compare that to 100 amps, you see that the cross-section is quite already half, and that's something that you have to take into account. So from the high voltage perspective, the reason why industry is moving to that are enormous. I'm here just illustrating by a couple of examples in order just to show where we are and how the overall strategy behind is and what you have to remember. However, when we speak about a battery pack, we have also to understand that for every battery that is coming out from the factory, the battery cells are not 100% equal. There are differences between battery cells due to the manufacturing processes and etc. So we need a battery management system which can monitor and also balance the differences between the battery cells in a proper way. And that is why typically we say that the battery management system has two big roles. It's a monitoring one, and then the action one, which is actually the balancing. And then it is playing a key role from the safety perspective, because it is collecting all the data. It's collecting all the data, it's processing the data, it's communicating with the different another systems in the vehicle. It's also storing data where they can be analyzed, but also data are very useful for activating another solutions in your battery system, like the thermal management, because battery should be cooled down, heated often, and also very key to activate the safety systems which are integrated in your full battery system. So there are different aspects here that are integrated, and here you see typically continuously there are quite a lot of sensors integrated in battery, where we are measuring voltage, current, temperatures, even pressures, etc., which should be monitored, processed in order to take the right action points. Now, when we come to components of high voltage battery packs, what you saw in the previous slide is just an example, and BMS, which is just monitoring, controlling. But in principle, in a battery pack, what you have cells which are connected in series to create a module, as you can see here. And then those modules are connected in series or in parallel to get the right capacity and the voltage. And then there is a thermal management, which will be activated in terms of what are the temperature conditions of your battery. Typically, it's preferred that the battery temperature will stay between 20 to 30 degrees. So cooling and heating will be operated accordingly. And the winter heating will be often activated, and in the summer cooling will be activated. As you know, in Spain, in the summer easily can be 45, even 50 degrees. So from that perspective, the cooling is a very key aspect. Then you have some switches, a round of switches in the battery pack, switch box and housing interfaces, quite a very complicated aspect. And then a lot of sensors behind that, which is controlling different of aspects as well, that you should know in that regards. So what does it mean? Moving from one voltage to another is not just affecting one part of the component, is actually affecting the full design of the battery pack, but also of the component as itself as well. So something that you have to know and to take that into account. It's not an easy aspect. Even if you dig further in the in the battery module, you see there is every battery module has also a kind of a BMS, which we typically say it is a slave BMS. And then inside the modules, there are also cells connected in series or in parallel, as you can see here. And around the modules, there is a housing. It can be metallic housing, it can be plastic housing or composite, depending actually what the needs are accordingly. So it is a very complicated process of design. And here, for illustration, you see what types of components do we have there: current sensors, high voltage switches, fuses, voltage sensors, current sensors, temperature sensors, isolation monitoring systems, etc., that are typically part of a safe battery system design concept. And it is continuously in interaction, monitoring, processing data, giving the right actions accordingly. And here, this system is playing a key role. Battery management system, BMS, is playing a key role. Typically, if this will fail, full battery pack is going to fail accordingly. Now, if we go further in the battery housing or battery systems, you have to understand that the housing, which is covering the battery modules and even the full battery pack, is playing a very important role. Why? Because the full battery pack is integrated typically in a chassis of the vehicle, so insulation is very important. But also the weight of this housing should not be very high. So the lower the weight of the material that are associated to that, the higher the energy density will be. Then also what is very important in the design is that the ceiling should be quite very well, because typically the IP protection values for batteries are very tough. IP67 is typically recommended, or maybe higher, so that is something very important to take into account. And also typically we have pressures control to equalize the pressure inside the battery pack, because there could be some gases that could escape, so you need a pressure equalization and also condenser and handling. And as I said, you have a lot of interfaces or another type of component like the thermal interface, data plug, and the service disconnect and packs that should be also integrated in the full battery pack in order to fulfill the needs or the requirements of the design. In that regard, here you see an example of a pressure equalization, or where it will be activated when the pressure inside the battery pack can be high. Very key to have that, otherwise disasters could happen. And here you see an example how typically battery modules look like, where you see some numbers of cells are connected in series, and they are here from that side connected through bus bars, and there is aluminum frame around that, and you have typically the two outputs, plus and minus. Something that you should take into account, and you see here the BMS, which maybe it's not very clear, but the BMS associated to that as well. Further, what we see, of course, the full battery pack is much more complicated than that. So typically we have here modules which are connected in series or in parallel, depending how the voltage and capacity will be. You have the battery cover. Every module has a BMS. And you see here actually the cooling solutions or thermal management solutions that are associated to that, with all required cablings and so on. So the proper battery pack design is depending actually of the requirement and specifications in where you are going to use that. Here is an example of the liquid cooling concept, which should be allowing fast charging, but also working for allowing the battery to work in a wide operating temperature conditions. Further, more details, if we dig that. So, as I said, we have modules, but we have actually more another types of components. So here that are typically module connectors, which could be bus bars, which could be cables. We have here cell management controllers, the electronic, BMS, and then a lot of housing which are around that, etc. So it is all depending of solutions, designs, requirements, and specifications which are associated to the application, etc. So concretely, now if we dig further in the electrical components, we see if we go from 400 volt to 800 volt, of course, it's offering quite a lot of advantages, but also a lot of complications. And the design and the component and the manufacturing even, etc. First of all, 400 volt to 800 volt means more cells in series, and that means a novel types of BMSs that should to be developed accordingly, because all the BMSs that we have on the market are based on module level concepts where they can manage 12 or 15 cells in series. But of course, we can, if we go to 800 volt, we have to manage everything in one step. That makes the BMS much more complex. Secondly, the thermal losses will decrease. That's good, which affects the cost and weight and even of the bus bars, connectors, everything. But also it will improve the charging modes. Why? Because the current rate will be less, and the thermal management will be less sophisticated and also less heavy, and also will require less volume. Now, 800 volt means as well that the mechanical design should be completely redesigned from strength and stiffness, since there will be no any module housing, there will be only pack housing, and it will, of course, will reduce the weight dramatically, but the pack housing should be quite well protected. IP class should be quite very high, and this will affect definitely the battery pack cost. It should be resistant to corrosion and chemical materials. It should be fire resistant, definitely. And it should also be resistant against external forces which will could be applied on the battery during crashes and so on, and which will also increase the weight and cost, etc. So as you can see here, it's a combination of different pro and contras that we have to consider regarding the optimal design. The pressure is becoming very important. Where to place that, what will be the impact, etc. Handling the leakage, very important. So sealing is very important. Protection against hazardous parts by persons, and safety in accidents, in particularly when you will have a crash and such type of scenarios, which could be very dramatic. But does it mean also that there should be a clear focus to how to deal with the maintenance? Because right now, when we have modules connected in series, very easy. If there is a problem with one module, you take it out, you bring another one in. But when you have all cells connected in series, the situation is much more different. So it requires more focus towards the design and cost. Recycling, how you are going to deal with the recycling, how you are going to deal with the second life applications, which is also not easy, and you will see in the second part of the presentation. What is important to know is if you look to the cost breakdown of a battery, typically 50–60% of the battery cost is coming from the materials, which are the cathode, anode, electrolyte, and the housing of the battery cells. And then the remaining 40% is covering the rest, which is actually the battery pack. That means thermal management, housing, BMS, etc. that you have to consider. So it's very important to manage everything in a proper way to reduce the cost in something which is acceptable for the automotive industry. So in here you see the cathode is taking quite a big part of the cost, 25%, anode 8%, handling of cell manufacturing also 4%, battery pack management is 60%, and thermal management 8%, and the rest, yes, is just quite minor cost in the process, but they are also very important in that regard. So typically what you see in the automotive industry, that the OEMs, the car manufacturers, wants to do as much possible all this aspect by themselves, because battery is becoming a very strategic component or system in their drivetrain. Good. When we speak about battery, of course, first what you want is to have fast charging capabilities, which is one of the biggest bottleneck in the automotive industry. Nobody wants to stay too long waiting for charging. You want to have something which is equal when you are filling your gasoline and conventional vehicle. When we speak about fast charging, you have to understand there are different charging modes. We are typically about level 1, level 2, DC fast chargers, super fast chargers, and even there are some people which are speaking about extreme fast chargers. What does that mean? Level 1 means typically 1.9 kilowatt charging, which you can take it from household outlet. 120 volt EC, which is quite an uncommon voltage in the US and even in Switzerland. Level 2, 220, 230, 240 volt EC, which can go up to 19.2 kilowatts. And then DC fast chargers going higher voltage, 480, 50 kilowatts. And then you have also 480 volt for super fast chargers, up to 150 kilowatt with CCS connections. And then you have the extreme one, above, I would say, 350 kilowatts, as was illustrated in some of the examples a few minutes ago. And that is what you get here in this graph, that the charging time can be long or short, depending on which level you are charging, and also the allowing charging power is depending of the design of the battery pack. I will give you an example. Not every battery, not every vehicle, electric vehicle, can be charged at 400 kilowatts. Why? Because the BMS is the monitoring control, is a master control, which is deciding how much power that the battery can take. So if the BMS is already set that the maximum charging power is 50 kilowatt, then it will take only 50 kilowatt, even if the DC charger can provide 500 kilowatts. Doesn't matter. So you have to understand the interaction between the BMS and the charging is master-slave combination, where the BMS is a master and the charger is a slave, and the charger should provide what the vehicle is requiring. Now, what does it mean? In the beginning, when we started with the electrification, as I mentioned to you, we all started with 400 volt systems, DC, 50 kilowatt, which is state of the art, nothing special. Even 100 kilowatt is state of the art. That's not so big deal. And more, we start increasing the power level. We went to 150 volt, 150 kilowatt at the same voltage level, 400 volt. But you saw actually the current rate start increasing and the cables start becoming thicker. And at such a moment, we had even to cool down the cables. that was not more possible anymore. Then we start increasing the voltage towards 800 volts to allow 250 kilowatt charging to reduce the charging time. Then also to go even a step further towards 350 kilowatt in order to keep the charging time below 15 minutes, which was a clear requirement from the customer perspective or end user's perspective. And that's also what we see in the strategy of different car manufacturers. If we take here the maximum acceptance charging rate in function of the charging time, you see that there is no another way to reduce the charging time if you not increase the voltage level or the capacity. So from that perspective, if you want to have a limited charging time, then of course high voltage is an option, or increase of the capacity is an option, or the thermal management is also going to be something very important in that regard. So there are different parameters that you have to take into account in order to go from this scenario to this scenario. Now, of course, when we speak about fast charging, there are different ways to deal with that, or to increase the capacity of the battery, which I don't recommend because it's very expensive solution, or to apply novel cooling concept, or to play with operating conditions of the voltage. And we will explain now one by one what does it mean. Now, what does it mean? Increase of the capacity. Increase of the capacity means that you can keep the charging rate quite, or the current that will go through the battery limited, which will have less effect on the degradation. Consider this is the life battery capacity, and that is typically what you have, what you need for your operation, the blue one, and that's what you oversize for the aging, degradation, etc. So, and by oversizing the battery capacity is in a way, but it's an expensive strategy. Or going from 400 volt to 800 volt, and that can create actually a lot of advantages. Firstly, reducing the current rate, for instance, from 350 amps to 300 amps, and to increase the charging powers from 145 kilowatt to 250 kilowatt charging power. And something which is making fast charging possible at different levels, and even from the cooling point of view. So here you see a clear increase of the charging power by 70%, which is something not small. Now, what the reason for that is, it's all about the currents that are associated to that. So here, the currents are 4 times more, here is 2 times less, and that is affecting everything in one or another way. As I mentioned before, for the same power level, let's take power for the same power level like 150 kilowatt. If your voltage is double, that means your the decreasing the losses which are related to increase of the voltage by factor 4, and that's something that you should take into consideration. So for same power, voltage increase means decrease of the current, and you know for the losses it's I square. So I think I explained that the losses decrease will be quite dramatically, and that's how you can make fast charging possible. Are there any specific questions before moving to another battery pack design, which we call it actually cell-to-pack design?
I think that there are no specific questions right now.
Okay, so we can move forward?
Yes, sure.
Perfect. Cell-to-pack. So I explained in the beginning that typically commercial battery packs that we have right now on the market are composed of cells. Cells are integrated in module, and modules are integrated in the pack. Now, modular concept, easy to integrate, relatively easy to integrate, and there is quite a lot of know-how on the market in that. However, cells have already housing, modules have housing, pack and housing. What we are doing actually just placing housing inside and housing, which is actually quite design perspective and crazy and strategy. And novel strategy that are popping up, which we call it actually cell-to-pack design. What does it mean, cell-to-pack design? We are eliminating the cell house, the pack house, the module housing completely, and we go directly cell-to-pack. And that is being quite a lot of interesting approach, because if you look to those costs which are related to a battery pack, for instance, Nissan Leaf 22 kilowatt hour, housing still accounts around 4% of the cost. Wiring, harness, connections, interconnection, 5%. Battery managed systems, 8%. And overhead depreciation, even 7%. So even internal cell support, 5%. So a lot of high costs which are associated, which actually are not providing you any added value. So what I said at the beginning, typical approach are we have cell, we integrate in the module, and we go to a pack. So actually, you are not transporting batteries, but you are transporting mass. Now, what is solution to eliminate this completely and to go from cell to pack? And this will increase the energy density quite dramatically, and also will reduce the battery price quite a lot as well. So that is something that you have to take into account in that regards. Which is important. If you take this as a fuel tank, for example, above, for instance, and that is where you can fill your fuel. If you remove those parts, which can say it's equal to the battery module housing, you can have a better, more space that could be used, or to integrate more batteries and the same capacity in volume, or to reduce the size of the battery accordingly. So the advantages are quite enormous, and that's something that we have to take into account, and that can make the concept and the design of the battery pack quite dramatically different. And that's actually how Tesla started with. Tesla was the first one, pioneer in that direction, where they said, look, we have here a battery pack integrated in the chassis. Still, it was based on module concept, but the modules were not typically module of 24 or 48 volt. The modules were around 120 volts. So they were creating quite another times of large modules, and which are presented here. As you can see here, that are modules which are much larger than classically we know from the industry for Model S. And for Model 3, even they are not so many modules, they are only just 4 modules which are integrated in a full battery pack. What does it mean? You are reducing a lot of weight, you are reducing a lot volume, or you can incorporate more capacity to reach higher ranges. Also, if you look to Tesla, you see here, there is actually no cover of the battery pack. Why? Because they use the chassis the chassis as a cover for the battery pack to reduce the weight also further accordingly, and that's something that you should to take into consideration. Now, if we what we have to understand that if we want to achieve a higher energy density, longer ranges, we have to not only look to such type of solutions, but also to look to solutions which have at cell level higher energy density as well. And we see here a very clear trend on this graph, which is representing the volumetric energy density in function of the gravimetric one, a future trend towards 1000 watt-hour per liter, or 1000 watt-hour per kilogram, in order to enable the long range accordingly. However, such type of concepts, it's creating a lot of benefits, but also it's creating a lot of problems and challenges. Firstly, by connecting everything in series, you will have definitely much more complicated cooling system. And the reason for that is because the temperature distribution will not be equal. Second one, the mechanical design will be much more complicated. The pressure will not be equal, and the flexibility from the safety will not be there, because at the module level, you have still your own housing. It's also creating some safety level here. It will disappear. The time that you will have thermal propagation, can be a disaster. BMS, which will be much more active, much more complicated. It will be typically an active BMS, which more sophisticated hardware and software modifications that will be needed. And that means also in order to utilize the maximum volume in your battery pack, the most interesting designs will be actually the prismatic cells, because that is where you can utilize the volume in a very proper way, and with not loss in the volume accordingly. And also, prismatic one has hard casing, which are large in capacity, and also which is becoming a standard in the automotive industry. And for those that were following the Volkswagen Power Day, they could see that the prismatic cells are becoming standard. Now, when we mentioned that that cell to pack, of course, it's showing quite a lot of advantages, but from another side, it's also creating problems on such way. In particular, if we combine that with fast charging, 350 kilowatt, it means you need fast release of the heat in one or another way. And one of the concepts that is typically popping up is immersion cooling. What is immersion cooling? You have dielectric liquids in the battery pack, which is in a direct contact with the battery cells. And when the heat is created, the dielectric liquid absorbs the heat, and then it goes in evaporation mode, and then it gets in contact in the condensation plate, where it goes back to the initial process. Of course, this is not an easy process, because firstly, your pack should be perfectly leased. Secondly, it should be dielectric liquids. Secondly, this process is not happening in an optimal way, because still a lot of pressure equalization is needed in that regard. Another concept that could be applied as well is by using traditional methods, cooling plates, which should be overdimensioned and large, but what definitely could be used is integrating of heat pipes, potentially. for such type of solutions. That's one thing. But from the electronic side, as I mentioned to you, we don't have modules for cell-to-pack configuration anymore, so which is quite very easy here. We have to go to such type of concepts, and the problem that we are facing right now on the market is that they are not sufficient developed chips on the market available for such type of solution, and particularly chips for the BMS. So that is a further development which is needed. Sensing is becoming very important, but also wiring, because you cannot place all the wires through all the cables in order to not create any safety issues. BMS means there will be no any more master-slave combinations. It will be only one BMS that has to manage everything in a proper way, and that is quite a complicated process, from hardware, software, sensing, etc., that you have to take into account. What are the strategies to cope with that? As I said, smart monitoring is very key. As you can see here, smart monitoring is very key. The way how you are going to sense the parameters is very key in that regard. And also from the cabling point of view, how to integrate it in a smart way. So wireless sensing technologies are going to play a key role in this regard. Other aspect is about mechanical design, how to deal with that, how to cope with pouch cells, how to cope with pouch cells in a mechanical design for such type of applications. So you see here for pouch cells, it's not giving too much advantage because you need even a mechanical structure to cope with that. So the only preferred solution is the prismatic one that can allow you to keep the strength of the mechanical design and also the safety one. Now, if you place, of course, all the cells in series, you should take into account their insulation aspect should be covered. Something also the batteries could bulge, swell in that regard, or there could be some mismatching in that regard. So the cell should be integrated from that perspective, from the swelling point of view, in one or another way. And here, from that perspective, you see here upper and lower cell spacers are very key in that regard. Mechanical design should also to take into account the torsion problems and the tensions that could occur or could be imposed on the battery. Housing, cell housing of the pack housing, as you can see here, that is typically designed of a pack. To integrate your battery cells directly like that, and it will go through different conformation during crash or whatever. You could see what kind of consequences it could happen on your battery pack from the thermal or the safety point of view. So everything should be done in a proper way in order not to overlook anything. What we see also, it's not only cell module pack or cell to pack, there is also a new concept which is popping up. Why actually to have still pack housing? Why not even to reduce pack housing to go directly from cell to chassis as it is here, to reduce the weight much more further? That is also now a concept which is popping up, which is much more interesting from the weight perspective, but much more complicated from the safety and integration point of view, because you're eliminating every housing around the pack at all. So the chassis is becoming the housing, and that is actually nothing new, because if you look to the Ferrari cars, electric vehicles, they are already based on cell-to-chassis concept. So the cells are fully directly integrated in the chassis, and that's something that we have to consider as well. But it is quite much more complicated because it requires a full design of everything from A to Z, from safety, thermal, mechanical, electrical, etc. And that's making the situation quite much more complicated. But that's not something for tomorrow. It will be integrated in the automotive industry, but that will be something by 2030 forward. Are there any specific questions so far regarding this topic?
No question for the moment, I think.
No question for the moment?
No, you can continue on.
Okay. Now, safety. As you know, no one wants to have explosion in the battery pack or in the vehicle or wherever. So safety is a very key aspect. If you look to any requirements in the automotive industry, every car manufacturer will firstly tell you the first three requirements, which are safety, safety, safety. That is something which cannot be discussed at all, because nobody wants to have explosions in the batteries or in the vehicle. However, what you have to know, if you keep a battery, if you use a battery, any kind of battery in a proper way, depending the chemistry, LFP, NCA, NMO, LTO, whatever, and so on, if you use that in a proper way, you manage that proper way in terms of balancing, in terms of thermal management, and so on, no one of the batteries will ever explode or will get in problems. Typically, problems start when the systems are starting failing. Thermal management is not working properly, BMS is failing, dedicated components are not designed very well, or mechanical design is not developed well, as on. So if you keep the battery as it should be operated according to the data sheet of the manufacturer, and you keep the temperature between 20 to 30 degrees, everything is safe. When problem starts, when actually you start going outside the normal operating conditions of a battery. Consider you go over 70 degrees, what you typically have, you get your electrolyte is becoming unstable, it starts creating gases, and their chain reactions will start slowly. And that's what you see here. That is typically a process of thermal runaway. When battery starts initially failing, which you don't see that. It's internally it's creating gases and so on, and then slowly the battery temperature is increasing, and then when it reaches 100 degrees, then dedicated components in your battery system or battery cell start failing. And the first is failing, that are the protection layers that we have in the battery cells, which we call it passivation layers, start breaking. When this is increasing, separators start melting, you create short circuits, electrolytes start decompositing, carbons start breaking, solvents getting problems, and so on, and so on, and so on. When the temperature is increasing, as you see, you can see my mouse is increasing, and then you can to this area, and here actually where the problem starts. When the temperatures is around 1,000, 1,100 degrees, that's where you get an explosion, because the amount of heat at that moment is such huge that you cannot control it anymore, and it should get an explosion. And the problem is in the explosion, it's also that a lot of gases are associated to that, and that are typically toxic gases, hydrogen fluoride, phosphoryl fluoride, and carbon monoxide, that are typical gases, depending, of course, of the battery chemistry to chemistry, that are getting out and which are toxic and are affecting our health. So that is something that you have to take into account. This process from here to there, it can take a couple of minutes, but sometimes even it can take days and weeks for your information. But again, if everything is handled in a proper way, there should be no any problems in that regard. What does it mean? Not every battery go directly in explosion. There are different classifications of thermal problems, which we typically call it abuse, thermal runaway, and propagation. Abuse, when typically during crash, you get deformation of the battery pack, and which affect the battery cells, which could be overcharged, over discharge, or overheating, etc., that are typically not normal conditions of the battery. And then typically we call them the mechanical design with a crash, penetration, and the over discharge, the electrical abuse testing, and the overheating, where you go over high or low temperatures, the thermal abuse conditions. And then thermal runaway, typically it starts from perspective of chain mechanisms. There is a one cell which is not in good condition, and it starts affecting the nearby battery cells, and that's where actually you get the propagation. And that's where chain reaction is happening, and that's what is actually, and it's representing also this slide. Consider here a crash is happening. Yeah, you get an abuse, and then it goes in the runaway slowly, and then you get the propagation, and then on it all you get actually an explosion at a specific moment. That's something that you have to take into account. It's not a straightforward process, but it is what it is. And for cell-to-pack configuration, this is dramatic. This is a dramatic situation because you have many cells, 100 cells, which are connected in series, that will go in chain reaction of thermal runaway solutions, and which will affect the performances. Now, what could be the contribution to abuse conditions? As I mentioned, that could be external heating, where temperatures is getting very high, of overcharging. Typically, batteries for NMC is maximum voltage around 4.3 volt, LFP 3.8 volt. If you go over that condition, then some elements are becoming unstable, of over discharge, extremely high current charging rates, or you have some structural damage or external short circuits. Typically problems that are happening. And what does it mean? It's affecting numbers of processes in your system, or reactions like the electrodes are not stable, electrolyte also not stable. You get the composition of your electrolyte. Electrochemical reactions are not becoming stable due to the many side reactions that could occur. And then, yeah, the consequences, as I mentioned, failing of different components, which give you a disaster, which we call it thermal runaway. Firstly, it starts with a leakage. Then you get smoke, gas venting, flame, explosion, and etc. So it's wide range of processes which are behind, and nobody actually understood very much all the interaction between such reactions. Now, when we speak about safety, you have to understand that safety is also associated to levels, which we typically call hazard levels. If we start with 0, that means no effect. Everything is working properly, no problems, good. If we have hazard level 7, that means we have an explosion. And that is what we don't want to have. And in between, you have numbers of levels, hazard levels, that are associated to this process, which I explained here and here, and which are summarized here. So level 1 means the passive protection activated is damaging. Level 2 means you have a defect or a damage, but still no leakage or no venting. 3 means you have leakage, no venting, but you have fire or flame, no rupture, no explosion, etc. 4 means you have a venting, still no fire or flame, no rupture, no explosion, etc. 5 means you have fire or flame, but still no rupture or explosion. 6, you have rupture, but no explosion. 7, of course, you have the explosion. You see, there are different levels, and which are actually also indicating what types of battery is safe compared to others, and that are European hazard levels, which are well known in the automotive industry. So from that perspective, as I said, thermal runaway or safety is quite very complicated process, which is actually a combination of exothermic reactions that are quite very complicated from nature as on, where different elements are associated, active, let's say, anode, cathode, electrolyte, membranes, etc. And that is something that you have to take into account. It's not so something straightforward to know that. Here are some examples that you could see. A package of cylindrical cells, which we call it 18650, which are the format. And they were tested at 100 degrees, as you can see here. And you see what happened. You get an explosion when the short circuit was applied. And here you see what can happen even if you have another state of charge level like 30 degrees. So the way how you are storing batteries, the way how you are maintaining batteries have huge impact on the lifetime and the safety. And that's also what is illustrated here. That's what I explained before. When you have an abuse testing or not normal operation, you get a failure of different mechanisms inside your battery cell, and finally you get a thermal runaway. Typically, people, when they are asking me what we have to do if a thermal runaway is happening, and my answer is typically the same. Run so fast as you can, because the process is so heavy, so fast that you cannot stop it at all. So if you can run as fast you can, do it, because that's the only solution that you can do, because you cannot stop the process anymore. Now, what are the ways to prevent thermal propagation? Because that's the most important one. If it's happened, don't do anything, just run away. But what should be done in order to avoid that such type of things will happen? Insulation between the cells are very important to enable the thermal propagation will not happen. And there are different types of materials that could be used for insulations, aerogel, fiberglass, etc. that are very important to be integrated. Spicing. So there is also between the insulations, there should be sufficient place, air gap, typically between 4 to 6 millimeters, to make that possible, because also batteries can bulge, swell, and we have to take that also into account. What does it mean? Yeah, it is, of course, it is lowering the complexity and is ideal for when you are using prismatic cells, and it's creating quite a lot of higher performances. But of course, it will reduce the volume, the volumetric energy density, and also it could affect the battery lifetime to such extent. What also can be used is a fireproof box. There are different materials, even composites, which are resistant against that, which are key, and that you see some dedicated pro and contras. Immersion cooling to transport the heat as much possible to outside in order to keep the temperature of the battery quite soft, so that can eliminate the thermal propagation, at least. That can extend also the battery lifetime. It also enables fast charging. But yeah, since the dielectric liquid is also heavy, it will affect one thing, the volumetric and the gravimetric energy density, and it's also not cheap. What is also possible is by using thermal conductive materials to remove the heat as much possible, or to transfer the heat as much possible, and to create an homogeneous temperature distribution over the cell, and which can be transported through heat sinks, etc., to another place. So typically what could be used is a graphite cooling fines or aluminum plates that are typically solutions that can be applied. Or what we see more and more on the market is actually instead of using let's say cells in that shape, which we have it for Nissan Leaf, we use actually much more longer battery cells, like what are integrated in the BYD, as we call it, a battery blade. And the reason for that is that the surface area is becoming much larger, and it can dissipate the heat much better. That's a solution, also a very simple solution, because it's required only to cool the tabs and not the full surface, because that are the main stress factors here and there that are possible solutions from that perspective. Now, why to use such types of large cells? This can reduce the mechanical structure quite a lot, because they are already integrated in a mechanical housing. It's also very interesting from balancing point of view. Also reducing the space which are needed when you have a lot of battery cells connected to each other. So there are different aspects behind that, but also there are some drawbacks that we see that are right now only applicable for 100 volts, not to larger applications, because those cells are quite very long. Thermal management can be done only at cooling plates, but that typically should be more than sufficient. But of course, if one battery cell will start failing, it will affect the remaining one, and that is also one drawback. But the chance is quite very limited that will occur, because the surface area of such type of cells is quite large. You see here an illustration how they are typically integrated. Many cells connected through a large bus bars from that side, and the cooling is also happening from the another side. Of course, this also required a lot of focus in terms of safety and cooling, because it's not easy, and particularly when you apply fast charging. But that is something that should be done for any battery systems, and the new shape and so on, it increases the surface area, which is making the cooling much more interesting, and the short circuit current can be reduced at least by 10%. Last but not least, when we speak about battery system, we can also reduce the battery pack housing, not only by working with steel or aluminum, but aluminum is now the standard, but by working with more novel, reliable materials, lighter, like composites, polymers, or even another types of material like carbon fibers, etc., that can reduce at least the weight by 10 to 20% additionally. For your information, this configuration alone, the battery blade, as we call it, it can reduce the weight of the battery up to 50%. That is quite a lot of the battery pack weight, which is something very important and which will result to longer range. Also, the materials can be designed in a such way that it can cope even with thermal propagation or even fire, etc. So they could have different types of functionalities, and that is something which is important, where it also can be foreseen of the required structure in order to enable fast integration of prismatic cells. Another solution is by using aluminum foam as a structure, which has an advantage that has high performance, thermal performances. It's light. It is also very robust, and it can make the system much more lighter, up to 15%. And we see this solution is going to be integrated quite a lot in military applications, and why not to extend that to electric vehicles as well. Now, a battery is also can be imposed to a lot of damping, vibrations, and so on. So any material associated to battery pack design should be also very well designed from the manufacturing of damping, and that the vibration should not have too much effect on the mechanical structure of the battery. And there are also some dedicated standards which are dealing with such type of aspects. So concretely, what does it mean? In the beginning, we start designing battery pack housing based on steels, and then we move to aluminum, then carbon fiber composite, we see more and more, then new techniques to manufacture like extruded aluminum profiles. We see that like in the BMW i3, and more we are going to advanced concepts which are lighter, like composites, polymers, etc. But final selection of the material is based on one thing: safety, safety, and safety cannot be touched. Now, just to give you a couple of examples of prototypes that happened in the past. Here's a prototype of a composite for a battery pack, which was actually 40% lighter compared to the aluminum cover, which is not a small part. And Hyundai and other companies had also similar architectures in the past, but they never went in the commercialization. Are there any specific questions so far?
Do you have any questions? I have one question. One question related to that. You were mentioning that the industry was moving into large cells or large format cells. What happens with Tesla? Tesla is using cylindrical cells. So, in your opinion, which are the main reasons for using those cylindrical and small format cells?
Now, small cells means a lot of cells that should be then integrated in parallel, more connections, more problems to safety, and so on. Reliability, if you want to extend the reliability of system, you should avoid the numbers of connections. In that regard, what is key, we see on the market that there is a big trend to go to large cells due to the reasons that I mentioned before. The Tesla strategy is depending from region to region. In US, they are using indeed cylindrical cells, but Tesla in China is going to use lithium iron phosphate prismatic cells, large prismatic cells. And in Europe, in Berlin, China is going to use even power cells and prismatic cells. So Tesla is not bounded on one specific strategy, and in the long term, they are going to move to prismatic cells. And during the next slides, you will see why they are going to use prismatic cells in the long term.
Okay, thank you.
Any further questions?
No, for the moment.
Good. What does it mean? Let's look further to a couple of slides, what is going to happen in the future. Now to the battery technology. So if we take this slide, which is representing the electrical range and function of the coming years, we see that in the beginning, we started with electric vehicles, which we had a typical range of 200 kilometers, 150, 200 kilometers, and then we went 300. 400 is now becoming standard, and more we are increasing that with the ultimate goal to go to 700, 800, or even preferably 1,000 kilometers. Now, what does it mean? Here already we are touching the limits of our materials. And the materials that I discussed before, cathodes, anodes, and electrolytes. If we want to go in that direction, we have to change materials. We have to change cathodes, we have to change anodes, we have to change electrolyte, we have to come up with complete structure of the battery in that regard. What does it mean from cathode side? To increase more nickel. Anode, to replace carbon by more silicon, or to go to lithium metal. Electrolyte, to go to higher voltage, etc. And with the ultimate goal to go to the solid state technology, because we can improve the safety. So from that perspective, what we see here, you see a graph which is representing the different generation of battery technologies. So we have right now the commercial lithium-ion battery solutions or technology, which we call it generation 1 and 2. Then we have generation 3, which should be on the market by 2025. And then we have the solid-state technology, which should to come in generations, but the most logical one will be by 2028, 2030. And you see here the characteristics in terms of energy, gravimetric energy, and the volumetric energy density, and also what could be the consequences on the pack level when it comes to the cost. That's something that you should know. And step from generation 1 and 2 to generation 3 is quite straightforward. But the step from jump from generation 3 to generation 4 is completely different. New skills, new technologies, new infrastructure, and so on. What is now solid state? If we look to this graph picture, typically you have cathodes, anodes, liquid electrolyte, and separator. Solid state is actually, you have still the same configuration where you have a cathode, if you have an anode, you have cathode, you have an anode, and the liquid electrolyte, we are replacing that by a solid electrolyte. This solid electrolyte could be ceramic, or it can be fully polymer, or it can be sulfide, whatever, which can extend the safety level quite a lot in that regard, but it still have a very specific problem. Since the electrolyte is a solid electrolyte, the ionic conductivity is very low. It's very low, and it cannot meet the charging requirement and the acceleration requirement that everybody is looking to it. And from the integration point of view, it's very easy. However, from the manufacturing problem point of view, is very difficult and very complicated. So it's a future which is in front of us, but it's definitely not there. We are a company, we are working hard on that, and we know how difficult it is to make it. Now, when we speak about battery, you have to understand as well, we speak about materials, and materials are often not available in Europe. And in those materials are some critical components. I mentioned cobalt, I mentioned graphite, I mentioned lithium, I mentioned manganese, I mentioned nickel, etc., which are typically components that we use in batteries. Cobalt is a very critical material because 65% of cobalt is coming from Congo in Africa. Graphite, for 90%, natural graphite is coming from China. Lithium is coming mainly from South America. And so here, it's not only about the technology, but it's also about the supply chain behind that, where we have to care that the materials supply chain is not in danger, and that is something very complicated aspect. Which means, if we look to this world map, and if we look to all the available materials, lithium, cobalt, nickel, or another materials, we come actually to the conclusion that Europe is quite extremely poor from many materials that we have compared to what is already existing in South of America, North America, Australia, or Africa, or even China and Russia. So all of those countries, they have something more or less, but unfortunately, in Europe, there is still, it's very poor in such type of materials delivery. And that's something very problematic. That means we are often depending of China for graphite, or of cobalt from Congo, or from another place, or lithium from here or there and there. So supply chain is something very important. And in order to secure that, you have to understand also making batteries means also we have to recycle batteries in order to secure the materials which are associated to that. Just to give you how complicated the process is, if we look to the collection rate of batteries in our cell phones, laptops, and so on, we will come to the conclusion that only 10% of all these batteries are collected. 90% disappear somewhere in the garden, in the garage, in the living rooms, or sleeping rooms, whatever. So we need a more coordinated strategy about that, and that's actually what European Commission come with, that every battery for electric vehicles or for vehicles that will come on the market, to the end, it should be as well collected and recycled. Last but not least, that's my last slide for this session, is the fact it's not only about manufacturing and recycling raw materials, but it's also about how you are manufacturing and how you are recycling. Because if we look to this graph, which is representing actually what are the CO2s emitted if we produce 1 kilowatt hour batteries. Here, Poland, for instance, if Poland wants to produce, and they are doing that already, batteries, we see that for every kilowatt hour produced battery, they are emitting 650 grams CO2. Look to Spain, it is 290 grams CO2. Look to Italy, 310 grams CO2. Germany is very worse, 410 grams CO2. Look to France, because they have a lot of modern nuclear power, 40 grams CO2. Look to the best of the class, Scandinavian countries, 20 grams CO2. What does it mean? The sustainability of production of batteries is depending actually of how green your electricity mix is. We know in Germany it's not the case. In the Netherlands it's not the case. Even in the Belgium it's not the best one. But those guys, Scandinavia, they have a lot of renewable energy and hydropower, which is actually enabling them to produce batteries in a very green way. And that's the reason why Northvolt is established in Sweden and not somewhere else, because they can take the majority of the energy from the renewables in order to achieve this target of European Commission to produce batteries in a green and sustainable way, which is below 30 grams CO2 per kilowatt hour. And what does it mean, 30 grams CO2 per kilowatt hour? It means actually that China can never fulfill this goal, because Chinese CO2 emission is around 1,000 grams CO2 per kilowatt hour. Why? Because the energy mix in China is based on all coal plants, and they will never be able to target that, at least in the near future. So sustainability is a very wide strategy, which different aspects are involved, from where you are taking the energy, which type of material that you are using, how you are going to produce it, how you are collecting that, how you are going to recycle that, etc. So I was trying in this session to give you a general overview. What does it mean from perspective of battery, that you will get an impression. What does it mean also sizing, what the technology, what we are expecting in the future. And that was my last slide for this session, and I am now open for questions.